Hello, this is Peter Yerkett. The next topic in text mining is that we're going to cover is classification, document classification. And this is basically what information retrieval does with search engines. Your search string will define documents that you're interested in and documents that you're not interested in. And so those are two categories, and for every document that is in some kind of a search target, all the documents on the internet or whatever, are classified into two classes, ones you're interested in and ones you're not interested in, and the search engine will try to find all those documents that fit into the interested category. Now that's a pretty fuzzy notion because first of all, the search string does not completely describe what you're interested in. Obviously, the longer you make it, the more accurate the search engines can be. But just because you put in a bunch of words, let's say you're putting in a search string of 20 words, doesn't mean that the documents which have those 20 words as their most important frequency. Remember, frequency is not a completely hard notion in the sense that we don't want all the documents in a group that have every word in them, or word in every document, just like a word in a single document. On the other hand, for search engines, if the search string has a unique word that only exists in one document, well, you're obviously going to find it very accurately. But again, those are rare situations. An example in our current course is the serious variable, being yes or no, are two categories, and so what we would like to do is to see whether we can predict the value of serious, yes or no, for a patient who was not part of the data. So document classification is, first of all, a supervised learning method. The idea is that we have a whole bunch of data, like our VAERS file. We partition it into training, validation, and testing sets. We definitely keep the target variable for the training set. So the training set has the target variable for every observation. The validation set has a target variable for every observation, and we use those two partitions to build the model, and then we apply the model to the testing set, which by the time somewhere around 10 or 20%. And we do this repeatedly. Very often we take 10 different samples and cross-validate them 10 times, and we come up with a model, and we pick the best model that predicts the new instances. So the testing set is the one that uses data that was not used to build the model, and that's how we measure how good the model is. Obviously, applications are to a patient. One of the things that doctors often tell me is that the same 20 symptoms apply to 17 different diseases or conditions. And so even medical classification as to serious or not is not an infallible classification scheme. Documents, I mentioned already. So this is generally what prediction does. Your textbook, Weiss, Inderkaya, and Zhang, is actually targeted toward classification. The entire book The third chapter is the chapter on classification, and it is sort of the reason for the book. There are many algorithms. Probably the one most people are used to is you take all the variables that are associated with a vaccination event, and we certainly use all the numerical and categorical variables like age and gender and so on. And then there's a text variable that are the doctor's notes. Whether we use the two together or not in the same prediction algorithm is an open question. SAS itself does not do a very good job, and very often doesn't even allow you to put a text variable into the classification procedure. There are other ways of getting from the text whether something is going to be serious or not, and that's done with a text rule node, and we'll get to that one. However, there might be algorithms in the other software that people use, Python and R, that allows a text variable to be used in the same algorithm that uses all the other variables like age and gender. So that has to be determined. SAS is not the greatest in at least Enterprise Miner and Text Miner at combining the effects of text variables and the other variables. Probably the most powerful algorithm for decision trees and rules is something called C5.0. This was developed by one of the pioneers in this area, and the algorithm had a variety of versions, and the last public version is C4.5, and that one is probably the one that's being used in Python and R and Java, because when 4.5 was improved to become 5.0, the author finally decided, well, I'm going to make some money out of this, so he sold that algorithm to people like SAS and IBM and Oracle and SPSS and so on. So C.45 is in the public domain, and you can play with it if you pick software like Weka. Weka has an quote improved version of 4.5. Whether it's 5.0, nobody's saying. CART is so actually regression is probably the most commonly used one. You take all the variables, you make them all numeric, like I showed you with the 1 and 0s, and you run a regression. Now the trouble with text mining is that we might have, in this case 30 or so numeric and categorical variables and 200 and 300,000 words in the text variable. So we're talking about a regression involving thousands of variables, and it's not clear that, first of all, the matrix inversion algorithm that's used in regression is going to work very well for that many variables. The likelihood of having the matrix be a singular matrix so you can invert it, or nearly singular, becomes very high in cases like that. All you need is two rows that are identical to have a singular matrix, and so let's question whether regression really does work well for decision trees or not. CART is so anyway, the C algorithms, the CART algorithms, and these other ones support vector machines, neural networks, genetic algorithms. These essentially work with information, and many of the procedures involved entropy the reduction entropy, maximum entropy, whatever they're called. And many of them work very well. For numeric classification, so support vector machines is among the best. And nowadays, with neural networks involving multiple hidden layers of possibly thousands of intermediate nodes, we can fit pretty much anything. So the deep learning algorithms are very good, and they've all been applied to classification. I'm pretty sure SAS uses 5.0, and so what it does is it then builds a model, so we have a testing set. It predicts all the categories that the members of the testing set belong to, and that then allows us, and since we know the answers to the testing set, we now are able to see how well the algorithm does. And obviously the hit rate is, namely, predicting true positives given given how many there are, is a ratio. Can be greater than 1 because you can predict false positives to be positives. And the confusion matrix gives you how good each category is being predicted, and so on, and other measures. The explainability of a prediction is generally given in terms of a rule, and the output of a decision tree can be turned into a rule, into an if-then rule, and I'll show you how to do that, how to evaluate it. By and large, it's a divide and conquer method. You begin with all data in the trainings, in the root node, and we then have an a priori probability. In other words, given the data set we have with Sirius as its dependent variable, all the data might have Sirius to be 60% of the data, or 30%, and then the other portion is not Sirius data. With 3 categories, you might have 20, 50, and 30 probabilities in 3 categories. What you look for then, and this is the C5 algorithm, or the C4.5 algorithm, it finds the one variable that improves this percentage that's close to its actual, which we know in a training set, and it splits the data according to the values of that variable. So, for instance, if gender is a next variable that improves the prediction, the maximum of all the others, we then split the data into gender, male, female, and whatever other categories you want. And then for each one of those, you find use as the next variable the one that splits that one up into the best divisions. And so what you get is a tree. You start with all the data, you split it into all the values of the next variable, and then all the values of the variable after that. Now each node after the first split may have a different next best variable. So, for instance, if you split on gender, the male split might have as its next variable something like maybe a physical measure, a weight variable. Heavier people have different predictability than lighter ones, whereas the female one may have something like genetic history, racial or family history, and so on. So as you go down the tree, every level might be split by a different remaining variable. And you keep going until you either run out of data, in other words, there is no more to split, or you go into another level below and it doesn't improve the predictability by a criterion. In that case, you quit. Now, it's entirely possible that doing this will get you a whole bunch of leaf nodes that really don't matter, in the sense that, one gives you a 33.3% accuracy, the other gives you a 33.8 accuracy. Big deal. So you then prune the tree up to some reasonable level of accuracy. The result of all this looks like this in SAS. You have a root node, and I didn't put it at the top because I wanted to show the other nodes. So pretend like this root node, which classifies Sirius into 50.35 and non-Sirius into 49.65% of the data, which means that it's sort of almost flip your coin whether you're going to have a serious effect or not. And so pretend like this upper left-hand corner node is up here where the C of classification is, and then it branches into a variable called recovered, which can be yes, unknown, or missing, or it can be no. And when that happens, the leaf node on the right becomes a pretty pure node, and you find that 72%. If recovered is no, then 72% of the time the variable is serious, and 27 not. And if you need more variables, so after you say recovered is YU or missing, you then check on sex, female, male, or missing, or unknown, and then after that the funding agency might make the difference, and eventually you get to leaf nodes. And the leaf node is the then part of a rule. So if you follow a path, let's go down to here to 5. I've got it over here. So if recovered is YU or missing and sex is U, then the 70%, then 75% will have a no as serious, and 25% will have a yes. So this is the then part. Here, tree identifier 5, predicted serious 30, 70%. And obviously every leaf node has a corresponding non-leaf node, has a corresponding possibly leaf node or non-leaf node. But generally you're looking at leaf nodes, which are the conclusions, and then you follow the tree down until you get to a rule. So the rules look something like this. In node 3, if recovered is no, then the observations are yes and no in this proportion. Else, if recovered is YU or missing and sex is FM or missing, then predictability is 30% serious and 70% not serious. And this is the results that you want out of a classification. You want these rules, because now you get a whole new observation that had nothing to do with building a tree, and you can ask questions. Well, did this person recover? These are the obvious nodes, recovered or not recovered, because if you don't recover, you're dead, or you're hospitalized, or so these were kind of the obvious rules. The tree itself, if you run SAS on various data, usually comes out somewhere between 5 and 7 levels, and maybe 20 or 30 different leaf nodes. And then what you do is you check how well the model predicted. And to do that, we have several measures. The idea is that we define these measures by binary classes. In other words, the true class is either positive, namely yes, serious is yes, or negative, serious is no. And then we predict, and if we predict a positive node to be positive, then we have a true positive. If we predict a negative node to be negative, then we have a true negative, and these two are accuracy. A false positive is predicting something positive, namely serious, when it really isn't. And a false negative is predicting something not serious when it really is. Obviously, for medical work, the false negatives are the ones you want to avoid. Unless the treatment is worse than the disease, you can put up with false positives. Somebody goes to a doctor and says, I feel terrible, and the doctor says, well, here, take an aspirin, call me in the morning. And if they don't call, you might as well just give them the aspirin, because even if they're not sick, the aspirin ain't going to hurt them. So false positives may or may not be dangerous. If, on the other hand, a false positive is, well, you know, your chest pain could be a heart attack, we better go in there and do a bypass, and you then discover that once you get in there that no, this person did not have a heart attack, this person had stomach acid or something like that, well, then a false positive can be pretty serious, because you're doing operations and they're expensive and all that. So you can put dollar amounts or some kind of a value on each of these four. Obviously, a true positive and a true negative are the ones that you want to maximize, and you want to minimize these two. But whether you want to minimize the false positives or the false negative is something of a judgment. So, given counts, software will report each of these four. SAS, if you're running SAS, you go to the text portion of the output of the classification node, and it gives you these four numbers. Actually, several different ways, but you get these four numbers, and that's what you get by applying the model to the test set. Then, from these four numbers, we define various measures. Accuracy, obviously, is the number of true positives and true negatives divided by the total number. True positive rate is important, true negative is important. And then we have a couple of measures that came from information retrieval. They're called precision and recall. Recall is, did you get as many of the true positives as you could, the ones that people really wanted. Precision is getting them what the proportion of true positives is out of all positives. And by and large, people have come to the conclusion that if we combine precision recall in this particular manner, which is really I'm trying to remember what the name of this particular procedure is. I think it's, well, I forgot. But if you do this calculation, then the score that you get from like 0 to 1 or a little bit more gives you the best single number to predict the entire success of the procedure. And I've given you that calculation in something called the classification confusion matrix. So let's do that one. Let's look at that one. And in the middle of it, this is a huge spreadsheet. It goes from like row 1 to row 30 up into, you know, half the alphabet. The center are these four entries that the user puts in. So you run your software. If the software does not tell you what accuracy is, or sensitivity, or precision, or the F1 score, then you can use this spreadsheet, put the four numbers in here in the right place, make sure the true positives go in here, and then everything else is calculated for you. So accuracy came out to 57%, the F1 score is 0.47, precision recall is here, and precision is here. And then there are literally dozens of other measures, PP, PN, TPR, and so on. And I've given all these things names, but if you restrict yourself to the figures in red, you'll pretty much get how well the algorithm did. In addition, I've also added into the spreadsheet costs. So, for instance, if your benefit can be measured in dollars, then a true positive could be $100, a true negative could be $50. A false positive could cost you $75, and a false negative could cost you $40. And then you check the probability of these happening from stuff up here, and then you can get an expected payoff. In this case, it's positive. I could change it. If I make this 200, it'll turn negative. So this expected payoff is a expected value measure of making the decision at all. Obviously, you need a lot of data. You need these expense numbers, which you probably only get on average, and then there's a whole bunch of other measures that you use. So this spreadsheet, this confusion matrix spreadsheet, gives you pretty much all the measures, all the ones I would find until I got sick and tired of looking for more. You get a lot of measures, and most of the time you'll find that people will report some subset of these. So if we go back to this slide, you'll now have pretty much what you need to evaluate a particular classification scheme. So I'm going to quit here. Now there's two things we need to look for. The result of a decision tree, SAS decision tree node, are these rules. Notice they do not involve any of the text variable. So in the next slide and assignment and module I'm going to do, we're going to deal with text rules. And so SAS has a way of looking at just the text variable and the dependent variable, series, and come up with a set of words, combination of words that will make a similar rule, maybe without not necessarily being able to do confidence limit, confidence factors like 68% and 72%. So we'll get to that one next after this one. As usual, you're welcome to ask questions, and we can bring these things up in discussion topics and so on. Thank you.